Electrostatics 14th lesson, but today we'll go from electric dipole to a new heading, electric field strength due to continuous charge distributions. See, there is a scheme for yes.
Want we do some on electric dipoles?
We'll do. Well, we'll definitely do. Yeah, actually, I'll be giving you a very long assignment. But the lesson is actually, children, it's very huge, voluminous, the whole secondary syllabus in terms of the topics and as well the content inside. It is a huge lesson. Okay, that will come back. We need to move a little in the lesson. After that, the assignment will come. Okay, so the electric fields is due to continuous charge distributions. Look, why did we discuss dipole in the middle? I told you the simplest configuration was a single point charge. The next simple most configuration is a dipole. But next, of course, is quadrupole. Quadrupole thing we don't discuss here at intermediate level. But the most practical possible configurations are the charges, those are distributed on the bodies. Okay, so that's what the industry is will be looking for, right? So sometimes you face situations like this with the computers and whatever gadgets you've got. At the point where the wires are connected to screws, wherever, you feel some electric charges. You get some small shocks. Static electricity is formed, right? So we will be interested basically in charges, electric charges. Electric charges means excess electric charges, not electric charges. All the time bodies have got electric charges, but they're neutral. The electrons in the orbit and the protons in the nucleus are equal in number. But the moment you transfer electrons, that gets either positively charged or negatively charged. So our daily life is going to be affected by the electric fields formed by charges on the real bodies, either on the surfaces of the bodies, if they are metals, or in the volumes of the bodies, if they are non-conductors. So this kind of electric fields are going to be very important. That's what we're going to discuss today. Okay, look at that. We'll start. The heading is what? Electric field strength due to continuous charge distributions. But tell me, children, what kind of charge distributions you may have? You will have, look, three kinds of charge configuration, three kinds of charge distributions, let me say. Look, a line charge or a linear charge. Two, surface charge. Three, a volume charge. Anything else you can have? Nothing. Charge in one dimension, charge in two dimensions, charge in three dimensions. That's all. If at all you are looking at examples for this, look, line charge. What could be a line charge? You can think of a plastic sheet like this, a small thin sheet, and you can think of simply sticking charges to the plastic sheet. Plus, like this. This could be a line charge. Or it could be a metal wire, very thin metal wire, on the surface of which excess charge is formed. And what could be a surface charge? Charge that is distributed on a plate like this, for example. This is what you mean by surface charge. Okay. And what could be a volume charge? It could be charge is implanted, for example, in a non-conducting sphere. Why am I saying non-conducting sphere? Do you know? If it's a conducting sphere, charges won't remain in the body. They'll just go to the surface. So this is a surface charge. This is a line charge. This is a surface charge. Okay. This is a volume charge. So for this kind of charge configurations, we would like to find out the electric field strengths. Remember, when you are sitting in a room like this, in front of, say, a computer screen, and in the light there, and when currents are passing through wires, your body's cells are affected by all these fields, positively, negatively. I mean, for a good effect or for a bad effect, we don't know, including the radiation, that is the photons coming out of this light there, and also the screen here. All these things will have effects on our body cells. So to know the fields, which is safe field, which is beyond the safe limits, all that is going to be very, very important. Okay. So don't ever think that's just for the sake of some questions we are doing. These things have got practical use in your daily life and there in industry later. Okay. Now, but before we go to start to do anything, let me define three important quantities. Lambda, linear charge density. Linear charge density. I hope you are writing. Sai Bharat, are you writing, or you think this is not important?
Yes, sir. Writing, sir. I'm writing every point, sir.
Yes, right. Linear charge density, lambda equals dq by dl. That is charge per unit length. Charge per unit length. Sigma, surface charge density. This is dq by dA. This is called surface charge density. Then you also have volume charge density. That's called rho. This is sigma. This is lambda. This is now. This is one. This is another. And then volume charge density rho equals dq by dv. Volume charge per unit volume. This is. So this charge per unit volume, these quantities are going to be important for us to express elementary charges, for example, dq. Yes, Sai Bharat, you want to tell something?
Sir, what is the full form of that RH, sir?
Rho, that is Greek letter. Okay. This is rho, R-H-O, rho. Huh? That's R in Greek. Like you want to write Rama in Greek, it may be like that. Something like that. Huh? Mu. Mu is for M. All right. Okay. So three charge densities we define: linear charge density, surface charge density, and volume charge density. Why these things? Yes, we'll know now. Can I change the screen?
Yes, sir.
Okay. Now, look, the Coulomb's law we had is for point charges basically. Whether it is the field of a positive point charge, which we wrote as kq by r square away from it, or whether it is a minus charge, field of which we wrote towards it, which we wrote once again as kq by r square, or whether we wrote for a dipole, we considered the field of this separately here, right? That we might have got 2 kp by r cube for a small dipole, but that was found to be the superposition the field of this and fields. So everywhere we are taking point charge, and formula force equals 1 by 4 pi epsilon 0 q1 q2 by r square we wrote. We already mentioned that these are point charges, but in practice there are no point charges. Charges are distributed over the surfaces. Charges are distributed in the volumes like that, along the lines like that, for example. So you cannot hold up a particular charge and try to call it a point charge. So if I have a rod, for example, on which charge is there continuously distributed on that, if the total charge is q at a distance r from it, you couldn't have written kq by r square. You follow? Why? Because this is a point charge. This is not a point charge. The real charges are not point charges. Charge will be there all over. Okay. So we don't simply say that this charge is there at the center of mass and all that. We don't say. But instead, we'll take a dq charge, which is very, very small, almost approximated to be a point charge. Find out the field of dq and then integrate that field to get the field of the whole charge distribution. Do you follow that? I made a few statements. I want your feedback.
Understood, sir.
So the method is this.
Sir,
Yes.
sir,
Yes.
if
Parashara?
there are no point charges in reality,
Tell me.
means
Like,
what I am saying is that this formula kq by r squared, this kq1 q2 by r squared, that formula is there, no sir?
that comes like this. Coulomb actually
That
took,
is for point charges, right, sir?
yeah, I'll tell you. Like, how did he prove it if at all you get it out if there are no point charges? Spheres, for example, metal spheres, on which charges are distributed over the surface, can be thought of as point charges at the middle for the external field here. So Coulomb actually did an experiment with spheres like this. Because of the spherical symmetry, it looks as if the total charge is there and it is affecting a point, there it comes in symmetry cases. So this is likened to a point charge Q1, this is likened to a point charge Q2, but not all the time that you got spheres and then uniform distributions, right? So real charge is approximated to be a point charge. The real charge here is approximated to be a point charge. It is okay with this because when spheres are there, the behavior will be such a way that it looks as though this charge is there and affecting a field outside points. So that will be proving also in future. Okay. Parashara, tell me. So something I would like to mention
Yes, sir,
here.
that's fine.
For continuous charge distributions, continuous charge distributions, we find elementary electric field, that is small electric field, infinitesimally small electric field strength D due to a dq. dq is almost equivalent to point charge. From which formula? D equals K dq by r square, this formula, r cap. This is the field of a small dq, which is almost like a point charge. When I said dq is like a point charge q like this, I can write kq by r square, the field of that is dE. So the total field due to the whole charge distribution is integration of this dE. So this is the meaning of today's lesson. This is the summary of the whole lesson, actually speaking. So if I had, say, for example, this bottle, and on this, I go on rubbing like that, and then get some charge out of it. How to find the field of the charge around this bottle? You can't say the total charge is q and kq by r square, you cannot write. But a small place here you take, small dq, due to that you find out, and add up such fields all over the bottle, you'll get the field of the bottle. So that is going to be the concept, if you want to call it. How shall we do that? Okay, I'll continue, children. Rishita.
Yes, sir.
Boys.
Yes, sir.
Yes, sir.
Now let me see. Some maths we'll be doing. So keep watching, keep writing also, keep talking. Both, all the things do together. Now the first thing is electric field strength, that is E, due to a finite length of line charge. Finite length of a line charge. The first heading is this. Look at this. We have a line charge like this. Where could it be? It could be formed on a wire, metal wire, or it could be formed on a non-conducting sheet where you can think charge is there. Actually, right now we are not talking of the practical cases like how the charges are formed, all that. We'll come back to that later. We'll think that there are line charges like this. The reason is, wherever they are, finally, who forms the field is the electric charges. So you can think that you can line up few charges like that. The practical case would be like, where can you line up charges? That will be coming later when I discuss metals clearly. Okay. Are you catching my point? What did I say, children, just now? You can think of what? Lining up few charges like that, I told you. So look here, coming horizontal there. If I see, it is looking slanting. Okay. So you can think of some plus charge lined up like this. Finite length, not very long, not infinitely long. Okay. For this, I would like to find out the field at a perpendicular distance y. This is a perpendicular bisector. It doesn't look like that. I'll just change it and put it in the middle. Here in the middle of it, at a distance y, how much is E? Okay. You can think lambda is the charge density of this. What is this lambda here? Linear charge density, lambda per unit length, and suppose that lambda is uniform. So our job is to find out E at a point on the perpendicular bisector, a point on the perpendicular bisector, in terms of 1 lambda, 2 y, okay, lambda and y, that's all. This lambda and y only must be there in the formula. Some constants will come, that we need not bother. And whatever constants will come, they will come. 4 pi epsilon naught, whatever, all that will come on their own. Okay, so I want to get my formula for E in terms of lambda and y. This y distance is the perpendicular distance, lambda is the charge density. But remember, this is where? On the perpendicular bisector. No, let me tell you, I'll give you two more variables here. This is theta, this is theta. Okay, 3 theta. Since it's a bisector, both the angles will be same. So I want lambda in terms of, E in terms of lambda, distance y, and theta. Theta is the angle every this edge and that edge make with the point. So this is my main job. All right. So what do? I don't want to spoil this figure. I'll draw another figure here, because these are the things given in the question there. Like, I want to get the answer in terms of these things. So, but I have to suppose many other things in the middle, but those supposed quantities cannot come in our expression. So that's the reason, to distinguish between what are given already and what I'm going to suppose, I'm taking one more figure here. Okay. The space, okay, should be enough. I'll try. Listen, you should have a habit of listening to stories. Then you don't feel the pressure and you don't feel sleepy also. So this is plus. Now at this distance y, perpendicular bisector, we would like to find out E. So the method I told you already, we need to take a dq first. How do I take my dq? At a distance x from here, but taking this as the origin, I'll take a small element dx. So small that the charge on that is dq, which is like a point charge. For understanding sake, we put it so big, but it is actually very, 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 very small. Infinitesimally small. All right. So let me draw one line from here, which you call as R. This is dq. Tell me, are you following? Are you listening or sleeping?
Yes, sir.
Sir, charge density is dq by x, sir. Hello.
Charge density lambda will be
Hello, sir.
dq by
Charge
dx,
density dx.
not x. Huh? Okay. That's how we define. No, just go back and see. So tell me, due to this dq, what is the direction of the electric
Sorry,
field
your
there at
voice
that
is
point?
lagging a bit, sir.
Huh?
Your voice is lagging a bit, sir.
Internet connection. Others? Yeah, it will settle, don't worry. Now tell me, what is the direction of E here? Like this. Away from the point. Is it okay? This is dE. That's because of this dq, which is considered as a point charge. Okay. Come on. Let me say this angle is theta. Let me say this angle is theta naught. This is theta is a variable theta here. This theta is variable. These are the limits, known values of theta naught here. So we want to get in theta naught terms. Right? So dE will be like that, the way I showed the vector. What do you say? Similarly, exactly opposite element you take here. That will be there is one more dE there. Due to exactly symmetrically opposite element on the other side. I'll call this distance as r from the charge. Remember, that's not going to be longer than this. In length, that will be equal. This dE is because of this charge dq. Like that, for every two symmetrically opposite elements, there will be dEs there. But anyway, that's two are enough for me. This is also another dE, but magnitude will be same. Okay. So I want to find out resultant of all such dEs of different dqs on the either side of the origin. Oh, right. So I'll follow this components approach now. If this is theta, what will be theta, children? This is theta, is it? Opposite angle. So this component is what? dE cos theta. This component is dE sin theta. What do you say? Are you getting it? Similarly, if I take this one, the same theta it will be. So this is dE sin theta. This is in this direction dE cos theta. Is it all right, everybody? So all the opposite components dE sin theta cancel. All the dE sin theta components of symmetrically opposite dqs will cancel out. And all dE cos theta add up. Do you understand this? Tell me, I'll wait.
Understood, sir.
So finally, total E will be what? And you should also say from here that E is going to be vertically up, because all dE cos are vertically up. So the total E will be integral dE. Of course, here mod E I wrote, I'll simply write the direction anyway I mentioned separately, so I do not have to put a vector sign here. I'll simply find out the magnitude effect. D. Okay. D what? Cos theta. All d cos theta plus d cos theta plus d cos theta only becomes integral d cos theta. But how much is dE? But we know dE equals k dq by r square. This is dq, this is r. Right? that is r square. And dq equals what? Lambda dx. I've written it down here. Lambda is dq by dx, charge per unit length, by r square. So there are two variables, x and r, but I have got the variables as theta, theta. So I like to get everything into theta. The space is not enough. I should go to the next page. So until here, all the maths, whether you followed, you tell me.
Yes, sir.
So can I go to the, this is all integral, not over. I'm only writing d at. D cos theta we did not do it. So when I write it, I don't want to go back. You tell me what I've written down there. So we have dE equals, what do we have? K lambda dx by r square. Isn't it so? You're not even speaking. Is that the one we wrote? Right.
Yes,
Yes,
sir.
sir.
Now I want to get everything into theta terms. I want to get all this into the variable theta. For that, I'll write something from the figure there. Look at this. Tan theta is what? X by y. Cos theta is y by r. Will you remember this? So tan theta is what? X by y. Am I right?
Yes, sir.
So x equals y tan theta. So dx equals y secant square theta d theta. Tell me.
Yes, sir.
And we
Yes,
also
sir.
have cos theta equals
Y by R.
y by r. So r equals y by cos theta. This one and this one I would like to put in here. Okay. So what do I get? dE equals K lambda y secant square theta d theta by r square. Y by cos theta is what? Y secant theta, right? So y square what? Secant square theta. So what do I get now? K lambda. Tell me. Y by
K
went
lambda
away.
d theta. Y d
D
theta.
theta by y.
Y.
Now, but our E was integral d cos theta. So this is integral K lambda by y cos theta d theta from minus theta naught to plus theta naught. Look at the figure. This theta is a variable. So this will be minus theta naught, that will be plus theta naught for x equals 0 here. So I'm integrating now all the d's. So what do I get now? K lambda by y. Integral cos theta d theta is how much, children? Integral cos theta.
Sin theta.
Sin theta. Between minus theta naught to plus theta naught. So what do I get? E equals K lambda by y sin theta naught minus sin theta naught. So 2k lambda by y sin theta naught will be E, and for the rod, sorry, for the line charge here, at this point, this E is like this, and with this magnitude, where theta naught are the angles made by the rod at the ends. Look,
Sir,
all
can
the
you
mass.
show previous page, sir?
Yeah, all the mass is important here. The way you do the mass only will make you do problems later.
Sir, can you go to the next slide? I'm still writing that, sir.
So, sir, I didn't complete this first
1
slide, sir.
minute, sir.
Yeah, complete it. And also children ask me, huh? Like the maths part somewhere you did not follow, just don't do it blindly. We'll be
So
doing
completed, sir.
many more things like this we'll do. Anshuman, Abhinav, Parashara, tell me. So I deliberately wanted the formula in terms of y and theta naught. Theta naught are the angles made here or there. Where? I wrote it wrong here. Theta naught are the angles made here. Isn't it? Look at that. The beginning, theta naught I am putting here. So don't write theta naught here. It is there and here, not here. If I take in terms of that, I'll get 90 minus that theta. But questions, children?
So then what are the limits, sir?
What are the limits? What do you mean by what are the limits? You want to know
So
the
you
meaning?
said,
You want to know the meaning of limits?
no,
Or limits are already shown, no?
Sir, you are saying something, sir, limits.
These are the limits.
You said something.
This
Sir,
x
I
equal.
couldn't listen. You are saying some limits. There was internet connection issue, sir. So your video was lagging a bit.
Here, the way I showed it was not correct. It should be like this. This is the line charge, right? I said, when I put the angles here. not here. They are here.
Okay, sir.
Suppose you want to express in terms of this angle, no problem. In the place of theta naught, you will write 90 minus theta naught. So it will become what you call cos theta naught here in terms of these angles. So in the expression we took, in the beginning we took, this is y, this is theta naught, this is theta naught. These are the limits. Limits of integration. But I leave it to you how honest you are. Even some small first year things, if you did not know, in a very quick time, I will tell you that. But if you pretend to know them,
Sir, SHM, sir. SHM bit, it was. I didn't listen SHM properly, sir.
ask people to go from the room. So theta naught here, right? And lambda is the charge per unit length. So can I continue?
Yes, sir.
Bharat.
Sir,
I'll wait, not a big deal, but Rishita, have you got anything to ask for?
sir, you said something what, sir? Hello. Sir, your voice is lagging a lot, sir.
Others? No, if it is lagging only there, it should be your internet connection. If it is lagging for all, my
No
internet
lagging,
connection.
sir. Sir, there is no
It's
lagging.
fine for me, sir.
Okay. Now can I
No
continue?
lagging for me.
Can I continue as asking?
Yes, sir.
Now, yes, when I have, I'll write this slightly in a different way. The same formula. This is our line charge, right? At a distance y, in terms of this theta naughts, I had my formula as, of course, first of all, E direction I'll show is like this only. This is the value of E. And this, how much did we write, children? 2k lambda by y sine theta naught. This you'll remember. But I can also write it in terms of, say, if I take this dipole's length as this line charge's length as 2a. That means this is A, this is A. I can write it as 2k lambda by y sine theta naught will be how much? A by y square plus this under root, isn't it? Sine theta naught is A divided by root of y square plus A square also. This is another way of expressing the same E. Where A is the half the length. So we are taking many cases from here and trying to write them in various ways. All right. Now, second is a limiting case I'll see. Say, for example, this y is greater than A, or 2a, doesn't matter. Do you understand what it means? Both physically and mathematically. Okay, if you look at that in a mathematical way, the expression 2e equals 2k lambda by y into A by, this A is very, very less than y, so I can ignore it. So what will I get? Tell me. Y again, root y square is, A is put 0, y. So what do I get now? 2k lambda A by y square, which is nothing but 2 into k into lambda is what? Total, if the total charge is q, for example, Tell me what is lambda? Q by L
2 by 2a.
2 by 2a.
2a, isn't it? 2k lambda k by 2 into a by y square. So what do I get? Tell me, how does it look like? Can you, if you say something from here, I say that you are following. You should have told, I did not listen anything like that from any of you. No. I'll just change my direction of the thing here.
Sir, I'm not able to understand, sir. Your voice is lagging for me a lot, sir.
So for a very, very large distance
something.
y like
Just
this,
listen that lambda.
when this A is very
Hello.
large, this is almost like a point charge Q. At a distance y, E will be kq by y square. That means it looks as if it's a point charge. So kq by y square immediately should ring some bells in your mind, right? We already wrote kq by r square. And we did enough number of problems on that. So remember, anytime you do something new like this, and their limiting cases are the known cases, then this result is actually correct only. Or in other words, this case becomes a general case of this special case kq by r square. I told you already, we cannot have point charges and we cannot write kq by r square, we wrote. But now, what kind of approximation you can make a point charge is? For example, this small comb you take, and this way rubbed charge. At a distance of, say, for example, 10 meters from here, I can think that this whole charge is a point charge at the center of it. That's what we showed here, kq by y square when y is greater than a. Come on.
Yes, sir. Understood.
Okay. Third case now. For an infinitely long line charge. For an infinitely long line charge. Could you tell me what will happen? Infinitely long line charge means it will be very, 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 very long like that. Somewhere here, infinity it's going, there is going infinity. Perpendicular distance of y, if I take, what will be this angle theta? For an infinitely long wire, what is this theta?
Variable, no, sir.
Like this is that one. So if it is here, it will be like that. This angle is like this. Somewhere here, it is like that. Somewhere there. So what will be that?
90 degrees.
I was waiting for you to say something. Tell me, children. Right? So therefore, the formula becomes what? E equals, go back to that original formula. In terms of theta naught, what did we get? This one, right? So E equals 2k lambda by y sine 90. So that is 2k lambda by y. That means for infinite long line charge means actually in practice it is very long. So this becomes 2k lambda by y. Speak, children. So these are all problems, Bharat. Which I'm discussing like theory. One formula is now written in many ways. Here, 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 or the little more. If I finished it, I'll come back with more cases of that. Tell me. What are you doing? Are you doing or waiting for me to change without asking you?
Sir, completed, sir. I told you.
How about others? Now, another case. This is completely, what called surprise for me that you people wait for me to start without telling whether you finish it or not. Okay. Now, at some point at one of the ends, for example, here, but this angle is theta. Now, what should I write? Theta naught. How much is E here? Or let me say this is infinite, this side. This kind of charges are, line charges are called semi-finite or semi-infinite, whatever. This side is long, but it is at this end I would like to find out E. If you can tell me how much is that, then you've understood it. The previous one, at least you should try. I've told something here. Now, if I give you something like this, how will you write E there? Now tell me. You try to make some attempt, not that you should get it.
So it is not fully infinite. Like
This side is not infinite. This side, this is infinite. No, the moment I put y here, this is finite only this side, isn't it?
yes, sir.
Tell me.
Sir,
Make a try. You do not have to get it.
2ky lambda, 2k lambda by y cos theta naught.
Cos theta naught. Y. Y like that. On what basis you told that? You tell me.
Sir, if right side one is infinite, it will be up to 90, no sir. Then angle will be 90 plus theta naught, no sir.
So this is 90, agreed. sorry, I mean that I should remove theta naught. Just a minute. This is 90. All right, agreed.
Sir, angle changes as point charge is changed, no sir. It is right side one is infinite, no sir.
Right side is infinity I put. So the angle is 90, I agreed. What about this angle? This side angle, see the equation was given like this. This is the line charge. This is theta naught. This is theta naught, I told. Now the moment this point is here, what will happen? What will be the theta naught and what will be this theta naught? This theta naught, you told 90, I agreed. But what about this one? 0. This theta naught is 0, that theta naught is 90. So tell me, what do you get in the formula? First of all, remember, actually I wanted to make some try. You go wrong, but you wrote something. For that, I want an explanation.
Sir, I took like 90 minus theta naught, sir.
90 minus theta naught. What is 90 minus theta naught? Where? For why? Which 90 minus theta naught? This is not theta naught. I put first finite, so that's it. I removed it. This will be 90. So 90 minus theta naught is what? I've got some 5 rupees. You've got 5 rupees. You'll say, I mean, that we have 10 rupees. For what reason? Unless you and may go buy something with 10 rupees. What is 90 minus theta here? Where is theta? Even when you try, you should have some reasoning. No, if it is wrong, also no problem. Now go back to this integration. We integrate from minus theta naught to plus theta naught. So now I should integrate between. Tell me. Look at that equation. Minimum thing is this.
0 to 90.
0 to 90. So k lambda by y. What was the integration thing there? Sin theta, right? Sin theta between 0 to 90. What do I get? K lambda by y sin 90 minus sin 0. How much is this? K lambda by y. So that should be the answer. Is it? No. It is not. You know why? Because when we did the whole integration, when we set up the question, we said we are talking about a perpendicular bisector and the opposite DQs, these components got cancelled, we said. These components are added up. So for this, actually, we written the formula now. Now in this case, what happens? There is no symmetrically opposite element this side. So these x components don't go away. Do you follow? So this k lambda by y will be only the y component you got. Here, this y component only you got k lambda by y. X component also will be there. Because this is positive charge, it will be somewhat this side. How much is that? We need to really calculate. Tell me. Remember that also will be k lambda by, because sum of these two things will be what? Root 2 k lambda by y. Sum of these two. That means the half lines net field is like this. So if I put half more line, that will be this way. Root 2 k lambda by y. sum of which is this way. Root 2 into root 2k lambda by y, 90 degrees. That is 2k lambda by y. I talked so much already. So what we're trying to tell is finally this one. It is k lambda by y this way. K lambda by y this way. We'll be independently deriving it, but I'm guessing from the old relation. So the net field is like this, which is root 2 k lambda by y. An important thing. Come on. The figures are all there, actually speaking. Rishita?
Yes, sir.
This k lambda by y is not going to be the total field. It is only the y component.
Got it, sir.
X component will be there because we took only.
There is nothing to cancel it out.
Yeah. So that X component also will be there, we said. But this and that are equal, I told. Why? Because their sum will be like this. And if I put one more full half here, even this will be like that. Same thing. Sum of these two will be the original formula 2k lambda by y. That's what I told.
Yes, sir. Understood.
Think about it carefully. If you wrote down all the 4 cases, just go back and derive it for yourself without looking into the notes. And while deriving, you get doubt, look into the notes. Then write the 4 special cases. And tomorrow you ask me, not tomorrow, day after tomorrow you ask me the doubts. In this heading, we did only one. There are few more, believe me. There's a ring. There's a disk minimum now, right now. So that way we'll be doing, if I finish at least that disk business, we are somewhat ready for a good number of problems. So is it okay? Can I close?
Sir,
Yes, tell me.
I have a small doubt, sir.
Why not? Tell me.
Sir, if line charge is made up of 2 different materials, then the density of the charges will be changed, no, sir?
2 different materials. Materials is not the point. You want to say I want to have 2 different line density to be changing?
Yes, sir.
Let it be changing. Still the formula will be valid, but the whole mass has to be redone again. Some more variables come.
Okay, sir.
The method will be same. Right?
Integration, sir, integrating D, no, sir.
Their X and Y components are there. Same. Method remains same. The numerical answer won't be same.
Okay, sir. Okay.
And then others. So I'll close then, right?